This is 6.3 part 1, exponential function notes. We are today, your objective today is that you can graph exponential functions. So, to kind of start things off with, what we're talking about are functions that are, well, they're exponential. And we're going to need to kind of figure out kind of what these look like. And we're going to start with what's the what's the general form look like? And so this is what we call that general form, because we always kind of have that general form of an equation. And so we have a couple aspects to this. We have this a, we have this b, and we have this x. And having an x in an equation should not be anything new to us. But the new thing for this is that this x is in the exponent spot, and that's the reason that's called an exponential function, is because that x, that variable that we often are changing, is in that exponential function or that exponent location. So we have a couple of aspects. So the first one that we have is a, and a is our initial value. And this is when x is 0. And it's kind of, if you want to think of it like as money, it's what you put into the bank on the first day. It's not what you get whenever you get your interest. It's kind of that initial, that very first kind of part of it. A lot of times this is used for population, and so this would be the initial population, 500 people, let's just say. Okay. B is our pattern, or what we're kind of multiplying by. It's going to be some type of multiplication, and that might be a little bit hard whenever you think of this, because there is a way for it to be kind of decreasing but still be multiplication. So we're just multiplying by a fraction. Something else that we kind of need to be aware of is it's kind of about this a. If our a is greater than 1, it's going to be a growth. It's going to be a growth model of some sort. And if our a is less than 1, it's going to be a decay. All right. In exercises 1 through 3, determine whether the equation represents an exponential function, or, well, I guess we'll just talk about what the other one is. And so if I look at number 1, I go, okay, y equals 9x. See, that means that this is going to be a linear equation. And the way that I check this is I'm looking at where the x is. The x is not at the exponent place, and so that makes this linear. And yeah, I didn't ask if it was linear or exponential, but it is kind of good to say, hey, you know what, this is linear. All right. Number two, we have the x in the exponential function, or the exponent location. So this is exponential. Y equals negative 2x, and this is kind of interesting because you're like, well, where's the a? The a in this case is a 1. All right, so looking at this, I have the x in the exponent location, so this is exponential. I always get myself tied up when I try and say exponent and exponential, because I always want to do one or the other. All right, determine whether the table represents a linear function or an exponential function, and write the equation. Write linear or exponential in the blank. Write the equation under the table. So the way to check to see if it's linear or exponential is kind of see how much it changes by. And what we're looking for is we're looking it to be a consistent pattern. And so to go from 5 to 8, that's plus 3. From 8 to 11, that's plus 3. 11 to 14, that's plus 3. 14 to 17, that's plus 3. 17 to 20, that's plus 3. And it's not quite enough to just look at the y's. We also want to check the x's and make sure that the x's are increasing by the same amount each time as well. So 0 to 1, that's 1. 1 to 2, that's 1. 2 to 3, 3 to 4, 4 to 5. Okay, yeah, that increases by 1 each time. So because we increase by addition, and and or subtraction by the same amount each time, that makes this linear. And so what I need to figure out is I need to figure out my slope, because we need to figure out the equation. So my slope, m equals my rise over my run, and I get 3 over 1. And so if I go, okay, y is 3 over 1, we are going to be doing, so this is 3x, and then I'm going to find my intercept, which has when x is 0, so this is a plus 5. Alright, then going to be going along, so 32 to 16, this is either subtracting 16, or I might think of this as dividing by 2. We'll see which one kind of holds up. 16 to 8, that's subtracting 8, so the subtraction doesn't work. 16 divided by 2 is 8. Alright, so maybe our pattern is dividing by 2. It's dividing by 2. And what dividing by 2 is the same as is dividing by 2 is the same as multiplying by 1 over 2. And that's kind of an important aspect to realize, is if we are, if we're dividing, we're really multiplying by a half. Or we're multiplying by 1 over that number. And so in this case, we have my initial value. When my x is 0, what's my y? My y is 32 right there. And then I have what my change is, which is 1 over 2. And this is all raised to the x number. Raised to the x. There we go. And so this is an exponential equation. I guess I should write that up there. Alright, number 6. 8 to 6, looks like subtraction. Subtracting by 2, subtracting by 2. Alright, we're subtracting by 2, we're changing by 1 each time. And so I go, alright, because this is subtracting by 2 each time, that tells me that this is linear. And because this is linear, I need to find my slope, which is my rise over my run. And my rise is negative 2 over 1, because my change each time was minus 2. And then my run was, I was changing by 1 on my x's. And so this is negative 2x plus, when my x is 0, my y was 8. Alright, let's go on to number 7. So first checking my x's, 0 to 1, 1 to 2. Alright, we're increasing by 1 each time. 2 to 6, that's either adding 4 or multiplying by 3. 6 to 18, that's not adding 4. Alright, so it's multiplying by 3, multiplying by 3, multiplying by 3, multiplying by 3. And so that, because it's multiplication, that tells me that it's exponential. And so writing this equation, my initial value, when my x was 0, my y was 2. My change is multiplying by 3, so I just put a 3 in here to the x power. Alright. Number 8. Evaluate the function for the given value of x. So, whenever we get this, we go, alright, my y equals 2, and all we're doing is we're plugging in a value for x. So 2 times 4 raised to the negative second power. We can evaluate this even without a calculator, because this negative 2 tells us that the 4 is on the wrong side of the equation, so it's 2 over 4 squared. and we get 2 over 4 squared is 16. And so we get 1 over 8. All right, when x is 3, so f of 3 is negative 3 times 5 to the third, which is negative 3 times 5 to the third is 125. And so we have negative 375. All right. Number 10 asks us to graph the function. Then it says y equals 2x. So if I make an xy table, and for the most part, whenever we're working with this, numbers that we typically use are going to be 0, 1, 2, 3, and also negative 1. And the reason for using negative 1 is it kind of just allows us to kind of see what's happening to the left. And sometimes that's good because of kind of whatever direction that we're going with. So if we start with 0, because if anything to the 0 power, so 2 to the 0 power, we know is 1. If I plug in 1, 2 to the first power, we know is 2. 2 squared is 4. 2 cubed is 8. And then, so the negative 1, if I plug in negative 1 here, oh, we're on the wrong side, so it's 1 over 2. So 1/2. And so I can graph this. And so I got, at negative 1, I'm at 1/2. At 0, I'm at 1. At 1, I'm at 2. At 2, I'm at 4. 2, 3, 4. And then I'm at 8. 1, 5, 6, 7, 8. And so I can graph this. And kind of an interesting thing about graphing these exponential equations, for now, for so far what we've talked about, is we actually approach but don't touch. We're going to talk about that in the next lesson. All right. Number 11 asks us to graph the function g of x equals 3, 2 of x, or 2 to the x on the graph for number 10. How are the y-intercept, domain, and range affected by the transformation? And so the big kind of change that's happening right here that is different from number 10 is that we have this 3. And so the question is how does that 3 change things? So if I graph this, so I'm going to make an XY table, and I'm going to do this one in purple. I'm going to use the same numbers, 0, 1, 2, 3, and negative 1. If I use 0, I go 3 times 2 raised to the 0, and anything to the 0 is 1, so it's 3 times 1, so this is 3. And maybe right now you can already see where this is going to go, in that 1 becomes 6, 2 becomes 12, and 3 becomes 24. And negative 1 becomes 3.5. And so if you don't see it, what's happening is we're multiplying every value that we had over here on the left that we had for number 10, we're just multiplying them by 3. That's what that 3 does, is it multiplies it by 3. All right, so if I graph this, so 0, 3, 1, 2, 3, 1, 6, 4, 5, 6, 2, 12 goes off the graph, negative 1, 3 halves. And so what we have happen is this definitely kind of increases faster. And kind of the main change, and it's asking how are the y-intercept, domain, and range affected by this transformation. The only real difference is that the y-intercept gets shifted up. And but the domain stays the same, and the range stays the same. Because we still have the same values for x, and then we have the same values for y. There is a way to change those, and we'll talk about that. at a later time. All right. Numbers 12 through 14, they ask us to graph the function, compare the graph to the graph of the parent function, describe the domain and range of f. So, in graphing this, we're going to choose some numbers. Okay. Let's choose x, f of x, and we're going to do 0, 1, 2, 3, negative 1. If I do 0, this is at 1. If I do 1, this is at 3. If I do 3, this is if I do 3, this is 9. If I do 3, this is 27. And negative 1, it's at 1/3. Okay. Graphing this, negative 1 is at negative 1/3. 0 is at 1. 1 is at 3. 1, 2, 3. And then 2 is at 9. 4, 5, 6, 7, 8, 9. And so it graphs asks us to compare. This comparison, it's going to be the same. And our domain is all real numbers. I believe some people like to write all real numbers as a cursive R. I can never do a cursive R right. Probably failed that part in elementary school. R goes from 0, so my range, and my range it goes from 0, because we approach 0, but we actually never cross 0. If you think about it, no matter how far I go in the negative direction with my x's, I'm never actually going to cross 0. I'm just going to get really, really, really close to it. And so this is, we're going to say the range is less than, or y is less than 0, or y is greater than 0, but less than infinity. All right. If we do the next one, if I do an x, y of this one, maybe I'll change colors for us. If I do an x, f, x of f of x, choose the same numbers, so negative 1, 0, 1, 2, 3. If I plug in 0, I get 1/2. If I plug in 1, I get half of 6 is 3. If I plug in 2, that's 36 divided by 2 is 18. If I plug in 3, it's a really big number. And it's not going to graph on here, so there's no reason to kind of really do it. If I do negative 1, I get 1 over, what does that wind up being? 6 times 1 over 12. So at negative 1, I'm at negative 1/12, just kind of guessing what that is. At 0, I'm at 1/2. At 1, I'm at 3. 1, 2, 3. At 2, I'm at 18, which is off the scale. And so I kind of come up, and it kind of grows right like that. So comparing this to a parent function, the difference of this is this 1/2, and what that tells us is that this is a vertical shrink. My domain still remains to be all real numbers, and then my range is still the same of y, or 0 is less than y, which is less than infinity. All right, let's do number 14. Number 14, we have x, f of x, and I'm going to go negative 1, 0, 1, 2, 3. So if I do negative 1, this one's a little weird in that if you do negative 1, it's you can think of this as like 1/2 to the -1 is basically what we're saying. And this effectively just kind of flips it. And so I go 2 times -2. And so that makes this -4. Because this -1 applies to both of them, and you get 1 to the -1 over 2 to the -1. Oh, they're on the wrong side, so you get 2 over 1. Just kind of clarification on why that happens. If I do 0, I get -2. If I get 1, I get half of -2, which is -1. If I do 2, it is, let's see, 2.5 squared is 0.25, and so a quarter of 2, so -0.5. And then 3, 0.25 times 0.2, or 0.25 times 0.5. Let's see here. I need to do it. 0.5 times 0.25. 0.125 times 2 is 0.25. And so what we got is when we're at -1, we're at -4. 1, 2, 3, 4. When we're at 0, we're at -2. When we're at 1, we're at -1. When we're at 2, we're at -0.5. When we're at 3, we're at -0.25. So this increases. Alright, and so if we compare these, the first thing that we notice is that the negative tells us that we reflected over the x-axis. And that 2 means that we had a vertical stretch. All right. And our domain is still all real numbers. And our range, instead of it going from 0 to positive infinity, we're going from -infinity, because that's kind of the end behavior of this one right here. So -infinity is less than 0, which is less than, and we go up to but don't actually cross 0. And again, we'll talk about kind of what that means and how that works. And I think I just realized I said something wrong at the very beginning. This isn't if A is 1 and less than 1. This should be B. Yeah, there we go. Sorry about that. So that concludes the lesson for today. Check with your teacher on what your assignment might be, and have a good one.